Hello. Today we consider a tool for correction of distortions in spectrum images. How we do that? For instance, we collected a stem image with Get and DigiScan tool, and in this stem image we select a green rectangular from where we are going to take spectrum image, either with ILS or EDX. And we do spectrum imaging, and at the end we extract from spectrum image elemental maps. We need some dedicated tool for that. In that case, I used Get and quantification tool. So, titanium, strontium, lanthanum, and iron maps. We already see some atoms, but you might notice an issue. The positions of atoms look rather distorted. And it is seen even more clearly in the dark field image, which is collected simultaneously with spectrum image. We can call it in situ dark field image. Indeed, the positions of atoms look not as what we expect for this lattice. Why it happens? That is because spectrum imaging typically takes time. In my relatively old instrument, it takes maybe several minutes, and during these minutes anything can happen. Drift can several times move the picture, and some other distortions might appear. That's all result in distorting the final image. But note that the overview image is not distorted. That's because it was scanned fast. I would say this green fragment was scanned only for a couple of seconds. So that's why there is quite regular lattice there. Now the question is whether we can correct distortions in our spectrum image data using this survey image as a kind of reference. And that is exactly what a new tool is doing. Let's minimize temporarily the maps and open a new tool, which is called SciCore. Here we are. Then we click at the survey image and at in situ dark field image and press tune. Then we have to confirm the sequence of the images. Image 0 dark field, image 1 survey. Okay. Now we have a kind of twin image. In the left, we see the dark field heavily distorted image, and at the right, we see the reference. There are also two rectangulars, red and green, and our task would be to position such rectangulars such as they cover exactly same area in both images. We can move rectangulars by dragging their corners. It's actually sufficient to move only two corners, for instance, left upper and right lower. And it is logical to put the corners at some recognizable features, for instance, centers of atoms. We did that with left upper corner, then with right lower corner. Please note that when we move red rectangular, the green rectangular moves synchronously, and that is very convenient. At that stage, they cover the same area. But we notice that the corners of green rectangular are not at the right position, and that is because of distortions, and that is exactly what we are going to fix. Let's move left upper corner. Right lower corner is more or less okay. But we have to ensure that both rectangulars now cover exactly same areas. For that, probably we need to count atoms horizontally 2, 4, 6, vertically 2, 4, 6, 8, and the same in the right image 2, 4, 6, 2, 4, 6, 8. Aha, this corner is not at the right position. It should be there. Now we can press correct. And you see that left image is noticeably elongated. Now it's generally fit the area of the reference. It was linear transformation, affine transformation. Maybe we can stay with that status, but we can also try to apply nonlinear correction. The whole image is divided on the number of vertical blocks. Usually the number of blocks is determined automatically, but sometimes system is not able to do that. Anyway, you have to control that and correct the number of blocks if necessary. You can make it smaller or larger. I think this number is okay because the borders of blocks are exactly at the atomic rows in the reference. Not that for the left image because of distortions. And that is exactly what we are going to correct. Well, we are certain with the number of blocks. Let's press confirm. Now we see a number of markers, green at the right image and red at the left image. And we have to position these markers at the right atomic centers. In this case, we start with green markers, and it's better to move these green markers as a group. Why as a group? Just because they are already spaced regularly. So moving them individually can only make situation worse. Okay, I think we position that more or less correctly. And now let's look at the red markers. They are not at the right position. We have to position each marker to the right place. Maybe something like that. Like that. Like that. Well, it takes time, but the result would pay off. Okay, now click the button warp. And you see that arrangement of atom is already improved. But there is still a couple of issues. For instance, look at that row. It is weirdly contracted. That's because during scanning it was some sudden vertical drift of the sample. So let's select the corresponding marker and press the button expand. Now it looks much better. The neighboring row in opposite is a bit too wide, so probably we have to contract this row by pressing this button. Well, it's already better, but still the arrangement, I'm not very satisfied with that. I think this is not the straight line. So let's try to correct the line of red markers such a way that it corresponds more or less the column of white atoms. Yeah, maybe like that. Press warp again. It's an iterative process. Still, I'm not very satisfied, but final tuning is better to do accurately. I think it's better to select a given marker and move it with arrow buttons. Something like that. Yeah. Again warp. Maybe this should be corrected more. Warp. Still. Okay. Well, you can do that a long time. Depends on quality you finally are going to obtain. But what is important? At the end, when you more or less satisfied with the results of manual tuning, you are recommended to press the button auto. Then it would be automatic correlation of left image and right reference image, which is the most objective result. Okay, now we are offered to choose the final area for our maps. It's worth to cut off these ugly wavy edges like that and correct accurately the upper and lower side. Then confirm. Good. So what we have? We have the corrected dark field image, but that's probably not what we finally want. Finally, we want to correct elemental maps. Note, however, that all deformation we have applied are stored now in this corrected dark field image. That's why it is called template, because it consists all information for correcting similar images. What we have to do further, we just assign this template to our map. It is assigned. We don't need template anymore. And let's open our elemental maps. Good. Now just click at the corresponding map and press apply. We corrected already titanium map, then strontium map, then lanthanum map, and then iron map. Good. By default, the resulted corrected maps are displayed in grayscale. You can also change it to color it. You can also change the contrast if you want, but that is already another story. Basic job is done. Okay, that's all what I wanted to share with you today. And then bye-bye.